I'm Jared Laddie, and this is Physics 2212 Lab 2 Charge Tapes. The purpose of this lab is to expand upon the findings of our first charge tape experiment by creating a more sophisticated model of the experiment. This lab models the tapes as line charges as opposed to the point charge assumption that we made for our computational model in Lab 1. And modeling the tapes as line charges as opposed to two just separate point charges, we found that the charge on the tape was equal to 2.6063 e to the negative 8 coulombs, which is about 2.06 times larger than the charge we found in Lab 1. Fundamental principles we're going to be using in this lab are the gravitational force of an object in Earth's gravity, Coulomb's law, which calculates the electric force between two charged particles, Newton's second law, which in this lab is that when the net acceleration of an object is 0, the net force on that object is also equal to 0. And some assumptions we're making are that both tapes have an equal charge, the charges on both tapes are evenly distributed, the tapes are both positively charged, and we're neglecting air resistance. Recap of our procedure in the first lab to get our measurements for this lab. We applied a base tape to the table, applied our charge tapes to the table and ripped them off quickly to give them their charge, observed their interactions between another tape. They repelled, so they're the same charge, and they were attracted to a negatively charged pin, so they're positively charged. And then one of the charged tapes was hung between two books, so it draped down, and the other was brought closer and closer to it until it began to float. And the system for that experiment are the two charged tapes, and the surroundings are everything else around it, such as the books and the table. So these are the calculations for Lab 1 as a recap, and our charge Q was found to be 1.26 e to the negative 8 coulombs. Here's the code for the computational line charge model. On the left, you outline your physical constants and import the mass of your tape that you measured. The original Q was found from Lab 1, and this big Q value was found through trial and error until the electric force on the top tape is equal to the gravitational force on the top tape. The E field function calculates the electric field of a charged particle at a given observation location using Coulomb's law. And this line charge function was given to us. It just creates a line of n uniformly charged points with a total charge, and it evenly distributes the charge amongst those. With our computational model code, right here we're initializing both of our charge tapes using the line charge function that we were given previously. This is also where we can put in our measured separation where the charge tape began to float, right here in the y part of the position vector for our top tape. And this n value is how many particles are being simulated, and the higher this number, the more accurate the measurement will be, but also the harder it is to run, so I chose 100. And down here, this E scale is just an arrow scale for the electric field arrows on each of the particles in the line. Part of our code is where we're calculating the total electric field and electric force on the top tape particles by the bottom tape particles. So we're just iterating through our top and bottom tapes and calculating the electric field by each of the particles in the bottom tape at each of the particles in the top tape, and then using our E field function, and then multiplying that net E field by the charge of our top tape to get and then summing all of those to get our net electric force on the top tape by the bottom tape. The final part is simply making a couple of visual aids for the computational model, including an arrow for our electric force, our net electric force, all of our individual electric forces, and our gravity force, and then just printing the magnitude of our electrical force and the magnitude of our gravitational force. Model created by our code, the purple vectors represent the individual electric fields on each of the top tape's particles. The red vector is the net electric force on the top tape, and the green vector is the gravitational force on the top tape. And we can see the magnitude of the electric force and the magnitude of the gravitational force are equal with the charge we selected. And some possible sources of error are some error in measuring the separation of tapes when they began to float in the physical lab, and the assumption that the tapes were perfectly in line with each other like they were, and they likely weren't when we initially took our measurement in the lab. In conclusion, what if the tapes were modeled like a single point charge like they were in the last lab? Like previously mentioned, when the tapes were modeled as a single point charge, the estimated charge on the tapes was 1.26 times 10 to the negative 8th coulombs, which is only about 48% of the charge we calculated in this model, which was 2.603 times 10 to the negative 8 coulombs. And these estimates differ because the first model was an oversimplification of what was happening in the experiments, because it treats all the charges as if they were concentrated into one point charge when they were evenly distributed across the entire surface of the tape. Because of this, the second model is likely to be closer to the real value because it actually calculates the electric field of a distribution of charges similar to the tape